Hello, this is Mr. Collier, and today we're looking at disjunctions. So disjunction is actually a fancy way of saying or, but we have two types of disjunction. We have inclusive disjunction and exclusive disjunction. So this is also called inclusive or and exclusive or. So you have two possibilities. In inclusive or, it's true when one or both of the propositions are true. So if either of them are true, then the statement is true. And here's the Venn diagram. Okay, here's the Venn diagram for that. And for exclusive, they're true only when one of them are true, not when both of them are true. So this intersection of P and Q here is when they're both true. So in this case, we do not shade that region for the Venn diagram. Okay. So here are the truth tables for exclusive and inclusive disjunction. So notice the different symbols here. That's exclusive disjunction and inclusive disjunction. So notice inclusive disjunction is true in three different cases here, when both of them are true and when one of them is true. Okay, so state whether each statement is each disjunction is inclusive or exclusive. So a square is a rectangle or a pentagon has 5 sides. That would be the inclusive disjunction. Okay, if we call this statement P and this statement Q, I guess we can call it P or Q. A square is a rectangle or a pentagon has 5 sides, but not both. Okay, so not both would be the exclusive disjunction. Alright, and the last statement here, dogs can play golf or 5 minus 3 equals 2. So that would be inclusive disjunction. Okay. Alright, next we have use a truth table to verify that P intersect Q naught is equal to P naught union Q naught. So this is in set notation. We can convert it to this logic notation as follows: not P and Q equals not P or or not Q. Okay, so that's what it looks like in logic notation. And see if this is true. We can fill out the truth table. So we have P and Q. We have the 4 possibilities of P and Q. And what we have here is not P and Q. So we start off by doing P and Q, and then we can figure out not P and Q. So P and Q, we have true, 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 false. Right? It's only false if both of them are. I made a little bit of a mistake there. Sorry. P and Q is only true if they're both true. So it's true, false, false, false. And here we have not P and Q. So basically just do the opposite of all these. If P and Q is true, then not P and Q is going to be false. And then true, true, true. So we've just shown here the truth values for the first part of our statement, not P and Q. And then we're going to do this for the right hand side here for not P or not Q. And we have it set up here with the truth table, and see what we can discover. So here we have the P values and then P truth values, and then we're going to look at not P. So it's just the opposite of these values: false, false, true, true. And for not Q, we're going to have false, true, false, true, just the opposite of these values here. Okay, so then remember this means or, inclusive or. That's only true, it's true if one of these two statements is true. So this is true, 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 and false here because neither of these are true. So there's our truth values for not P or not Q. And notice that the truth values for this statement and the truth values for this statement are the same. So we say that these are logically equivalent.